Another example, just to show you how exactly we can use p-value to make judgment. This is about college freshmen. So usually people observe for college freshmen during their first year in school, they gain weight. Their reasons can contribute to this. For example, it could be that for college freshmen, they now finally live by themselves. They can choose whatever they want to eat. If they don't pay attention to what they eat, they may gain weight quickly, right? It could also be that now they live by themselves, they change their daily routine, etc. So what is typically observed is that previous study find that freshmen usually gain about 15 pounds in their first year on average, and this is usually called the freshman 15. They gain about 15 pounds on average, and we also kind of label that as generation XL, right? Extra large. However, recently, a study by Purdue University found that this number, the 15, is actually changed to 7.8. So they found that the average weight gain by freshmen in that university is about 7.8 pounds, right? So the question is, with this new study, can we conclude that all university freshmen now gain less weight? Is this study typical? Is there sufficient enough evidence for us to say, look, now college freshmen do not gain as much as 15 pounds, they actually do better? So that's the question. Now, since the study is only from Purdue University, it's almost like this is a sample data. We need to ask, can we generalize what we find in Purdue University to the general college freshmen? And to answer that question, we need to perform hypothesis test. Using Purdue University study as sample data, we ask if the average number of pounds gained in the freshman year of college is less than 15. Because actually we observed 7.8, so we ask, is that really lower than 15 in general? Of course, if you compare 7.8 and 15 in absolute numbers, that's true. 7.8 is definitely less than 15. But this 7.8 only comes from a sample of students. And we want to generalize that to all college freshmen. And the null hypothesis we have here is that the average number of pounds gained in freshman year of college is equal to 15. Okay, so far, I only kind of described the null hypothesis in general. I didn't specifically tell you if the alternatives reflect our expectation, how do we set the null hypothesis? There are two ways usually people set the null hypothesis. One way is to make the null hypothesis totally complement to the alternative. That is, if we say in the alternative, the average gain is less than 15, right? For the null hypothesis, one way to set it is to make it complement to the alternative, saying that the weight gain is greater than or equal to 15. So that way, the null and the alternative complement to each other. That's one way to set it. However, for a certain reason that we will not discuss this in this course, to make the analysis and calculation easier, we actually tend to use the equal sign in the null hypothesis most of the time, ignoring the greater than for this case here. So we will not discuss this in more details. It's just a technical note here. And you may ask, well, look, if I'm asked to do the hypothesis, what sign do I pick? I highly recommend you to use the equal sign because it makes calculation easier, although I will not really ask you to do the calculation, but it's totally correct just to use the equal sign in the null hypothesis. All right, so with the hypothesis we have, let's perform the analysis. The analysis actually is conducted behind the scene here because we are not given the data. We're only given the result using some computer software. So we have the table here. Within the table, what you can observe is that, let's see. All right. So the p-value is given right there. It says it's 0.000. Basically, that tells us the p-value is 0, right? And you would notice that it says two-tailed right there. Two-tailed is kind of related to something we haven't talked about here. In hypothesis test, we differentiate between the situation where we have one-tail test or two-tail test. When we have one-tail test, basically that means in the alternative statement, we use less than or we use greater than. That indicates it's a two-tail test, okay? Now, in the alternative, if the sign is not equal to, then that's a situation where we have two-tail test. This is again going into the details of hypothesis test. It's not our focus right here. When do we have a two-tail test? It basically means if we have the sign, I'm gonna type it here, two-tail test. If the sign is not equal to, then that's a two-tail test. Well, look, we have one-tail test in our example. However, in the output, you are given this two-tail p-value. Very easy to fix. All you do is to divide this p-value by 2. That way you convert from two-tail to one-tail, right? So since it's two-tail p-value, you divide by 2, that's give you one-tail. You can kind of understand it that way. And therefore, if for the p-value of 0, if you divide that by 2, it's still 0. And recall that the criteria for p-value is that when p-value is less than alpha, we reject the null hypothesis. In our example here, p-value will definitely be less than alpha since p-value is virtually 0. And alpha could be 1%, 5%, and 10%. Whatever alpha you pick, p-value will be less than that. And therefore, in our case here, we determine to reject the null hypothesis. All right, and since we can reject the null hypothesis, now we can conclude that the average number of pounds gained in the freshman year of college is less than 15 pounds. So the conclusion for us to say is that the average number of pounds gained is less than 15. Okay, that's the conclusion for our test. So that's an example where you use p-value to perform the hypothesis test and make judgment about a statement. I want to show you one more example just to get you a little bit more details about hypothesis test, and that's about everything we want to talk in this course. I have more PowerPoint slides prepared. However, I'm gonna leave the more detailed stuff for your stat course professor to discuss. We are here again to kind of touch on the general idea here. All right, so suppose the Pizza Inn restaurant is concerned about store image before deciding whether to expand. Pizza Inn managers are most interested in how friendly customers perceive the service to be. A sample of 225 customers were obtained and asked to indicate their perceptions of service on a 5-point scale, where 1 indicates very unfriendly service and 5 indicates very friendly service. The scale is assumed to be an interval scale, and experience has shown that the previous distribution of this attitudinal measurement assessing the service dimension was approximately normal. Now suppose Pizza Inn believes that the survey has to be higher than 3 before a decision about expansion can be made. So what do we have here? Apparently the Pizza Inn is surveying their customers about their service, right? The higher the better. And they have a threshold. They say if the average score from the survey is higher than 3, then they can go ahead and expand the store. That's the idea. Now what left is for us or the researcher to use the sample data from 225 customers to judge whether the average satisfaction score is higher than 3. And when we say the average satisfaction score, we are talking about the average for all their customers. We're not talking about the average from the sample, right? And therefore, at the beginning, we're gonna need to state our hypothesis. We're gonna state what we expect. Of course, we hope the perception is higher than 3. So I'm gonna make certain correction here. This is the original sentence from our textbook, and I'm not quite happy with it. So I'm gonna make certain changes to serve our purpose better. All right. So our expectation or our hope is that the perception of service is higher than 3. That's something we want to test. And therefore, we put that as our alternative hypothesis. Or in mathematical or statistical terms, we ask whether the population mean mu is greater than 3.0. That's how formula we write it in statistics. Because we are looking at the average score for the whole population for all the customers, so we use mu to denote that average, and we ask if mu is greater than 3. For the null hypothesis, as I mentioned, 2 ways you can set it up. You can either say mu less than or equal to 3.0, or you can simply say the null hypothesis is mu equal to 3.0. That means we say the average customer perception of friendly service is just equal to 3. That's what we want to test. Now, if you are learning hypothesis in much more details in the STAT course, you will most likely encounter this stuff. It's the rejection region approach that we will not discuss in our course. I definitely want to leave something for you to learn in the STAT course. So we will kind of skip the rejection region approach. That's another approach you can make judgment. But I would rather we focus on the p-value, which is given here. All right. So we are taking a shortcut, which is not that good, but given the amount of time we have to do it. So the p-value for this test turns to be 0.00050 out there 1. And you can basically say this is 0. And this p-value will be less than any traditional level of significance because this p-value is less than 10%, 1%, or 5%, whichever level you pick. And therefore, this decision will be easy. If p-value is less than alpha, which is true in our case, we will reject the null hypothesis. So when we reject the null hypothesis, see what happens. If this is rejected, that means we find evidence in support of the alternative. And to translate that into the setting of our question, that means we find customer perception of friendly service to be higher than 3. Good news. Now the store, Pizza Inn store, can expand. So that's the conclusion we can make based on the test, and that's the recommendation we can give to the management. Customers do believe service is pretty friendly. All right, that's another example of hypothesis test. And finally, let me kind of flip through the pages and show you what a two-tailed test looks like. So I kind of mentioned there are two different types, one-tailed test and two-tailed test. If you see a sign like this, that means we're looking at a two-tailed test. And the reason we say it's a two-tailed test is really related to the reject region that we didn't discuss in this course. But basically, when you look at the reject region, if it's shading the two tails on this bell curve, that means we have two-tailed test. And by the way, I actually do expect that everyone has certain knowledge of this bell curve. It's basically denoting a normal distribution or t-distribution depending on the type of test you perform. That's a two-tailed test scenario. And if you go back to our pizza example here, we say this is a one-tailed test. I kind of change it to a one-tailed test. Ignore this part. This is the part tail shaded. That's the reject region we say. All right. And of course, there are more things about perform hypothesis, all different tests out there that we didn't discuss. You definitely learn more in your stat course. So that's all I have for this chapter about hypothesis. And this chapter should build the foundation for you to learn regression analysis in chapter 23, 24, and time series. Depending on the schedule, we may not cover chapter 24, but you definitely need this chapter for chapter 23, the regression analysis. All right, that's all I have, and I'll talk to you next time.